final lesson in this series is transformers. It links together some of the concepts we've learned. So a brief sort of reminder. Motors use the principle that a moving charge, a current in a magnetic field, experiences a force, and that turns the motor. And generators use the principle that a moving conductor with charges in it in a magnetic field induces an EMF, and in the generator we provide the movement either by us turning it or hopefully coal being burnt to heat water, to generate steam, to turn turbines. Today we're going to talk about a transformer. What is a transformer? How does it work? And how efficient are they? This diagram you should have seen in the lab in lesson time. This sums up what a transformer does really. I quite like it. It's an electric circuit in here which we call the primary coil, and there is no electrical link between the primary and the secondary coil. There is a magnetic link to the secondary coil, and the secondary coil is also an electric circuit. It's made of a cable, and somehow we get electricity, or we get a voltage, a potential difference from the primary coil, and we manage to transfer it to the secondary coil with some interesting changes along the way if we need it. But there is no link, no electricity flows around this core. It's a conductor, yes, it's iron, but it conducts the magnetic field. It does not conduct the current at all. So what is a transformer? Here it is. It's two coils wound around a soft iron core. The primary coil, this is the soft iron core. It's a laminated iron core, which means it's made up of lots of layers of iron, which we'll talk about why. And it's also magnetically soft, which we'll talk about why. And then the secondary coil is wrapped around the other side of it. And you can vary the amount of turns on these coil. An AC is applied, an alternating current is applied to the primary coil. It's got to be alternating current. Produces an alternating magnetic field in the soft iron core. Because you've got current flowing in this conductor, it's effectively an electromagnet. Because it's alternating, going forwards and backwards, it's a changing electromagnet, so it produces a changing magnetic field in the soft iron core. The soft iron core, if you like, transmits this magnetic field all the way around it, so you end up with a changing magnetic field in the secondary coil, or a changing flux linkage in the secondary coil. And we know that a changing flux linkage, then the rate of change of that flux linkage produces an EMF. The whole thing will not work on direct current. Why not? I hope you can see that the whole concept needs a changing magnetic field, and with DC you have not got a changing magnetic field. Okay, we did a practical in the lab with some numbers. This is what we did. The primary coil had 600 turns on its coil, and we applied a voltage of 0.8. And the first set of results here, the secondary coil had 300 turns, so we halved the turns. And what happened to the voltage? It went from 0.8 to 0.35, so it seems to be approximately halving the voltage as well. 4.4 down to 2.1, 6.7 down to 3.1. It wasn't a perfect transformer, but it did seem to approximately halve. If we keep the number of turns from the primary to the secondary the same, 600 to 600, then this column of data is showing that approximately it didn't alter the voltage. So 0.8 to 0.77, 4.4 to 4.25, etc. If we doubled the turns, so if we doubled the turns, if we go from 600 to 1200, then that's doubling the number of turns. And if you have a look, we nearly doubled the voltage. 0.8 went to 1.5, 4.4 went to 7.8, 6.7 went to 12, and so on. This is 600 up to 3,600. That's a factor of 6. 600 to 3,600. And if you look, we sort of nearly, again, it's not great, not perfect, we multiplied the voltage by 6. This leads us to the transformer rule, and this is the transformer rule which you need to know, and this is that the ratio of the voltages is equal to the ratio of the turns. If you double the turns, you double the voltage. Quite a simple rule, and you can get to it via experiment pretty quickly. Okay, so let's just look at exactly what's happening. A step-up transformer, this is the idea of a step-up and a step-down. A step-up increases the voltage, a step-down decreases the voltage. But from the equation year 12, power equals current times voltage, this isn't a magic power creation machine. The power has to remain constant, so we can't create power. We might lose a little bit of power, but we certainly can't create it. So if we've got power in is approximately equal to power out, then if we increase the voltage from this formula here, if I goes up, to keep B constant, we must, if V goes up, we must reduce I. So an increase in voltage will lead to reducing current, and a decrease in voltage will lead to an increase in current, because power needs to remain constant. If we did, taking this idea on a little bit, if we measured pairs of values of current in the primary and the secondary, and we measured pairs of values for the voltage in the primary and secondary, we could work out the input and output power. The input power would be Vp times Ip, the output power would be Vs times Is. Now, if we say it's 100% efficient, and it's a big if, but if we did say that, then the relationship that we would expect between these two would be that the power delivered is equal to the power supplied. So if we had 100% efficiency, we'd have this. We'd have that the Ip times Vp, which is the input power, equals to Is times Vs, which is the output power. The efficiency of a transformer is the ratio of these two. So if we take, this is the power delivered by the secondary coil, is what is the useful energy out, so Is Vs, and the total energy in, or total energy supplied, is going to be Ip Vp, which is the input power. If they're efficient, as I said, if we've got this the Ip Vp is equal to Is Vs, so this would be 1. The efficiency would be 1 for 100% efficiency. So we can quickly rearrange this. Very easily, we can just say that Is over Ip is equal to Vp over Vs, and using what we know about the ratio of turns to voltages, we can come up with a three-way relationship here, that this is the ratio of the current to the voltage to the turns. And notice that the Vp over Vs is equal to Np over Es. I've just flipped it from last time. So this is where the ratio of the primary to the secondary is the same as the primary to the secondary, but the current is reversed. It's the ratio of the secondary to the primary, because remember, as voltage is going up, then current must be coming down, and vice versa. So a bit of a summary on efficiency. Why might a transformer be inefficient? 3 reasons and 3 things we can do about it. The coils themselves might heat up their wires with a current flowing through them, so they've all got a resistance, and that could lead to heating of the wires themselves. Eddy currents within the core we looked at last session. If you've got eddy currents in the core, then those could cause the actual iron core to heat up, which is something that you won't want. And if the change in magnetic field, as the alternating current reverses the magnetic field in the core, if that's not sort of 100% efficient, so there might be some flux that you lose or escapes, we say. This is because it might not swap perfectly. So as it changes, there might be a sort of lag or a delay in the material itself that doesn't allow it to change as efficiently. But even with these 3 problems, we still get really high efficiencies. Even in the lab, you might get 90%, 95% or more. And large industrial transformers with cooling, oil-cooled, they can be up to 99.5% efficient, which is tremendous, really, if you think about that figure. To minimise these losses, to minimise ohmic heatings of the coils, we use low resistance wire in the primary and secondary coils. To minimise eddy currents, remember, which is the induced current in the core itself, then we use what's called a laminated core, which we mentioned. This is layers of iron on top of each other with sort of a small insulator between the layers, and this means that the eddy currents can't flow very far. If you stop them flowing very far, then you'd reduce that current, which reduces the heating effect. And finally, to make the change in field as efficient as possible, then we use soft iron, and it's the softer the iron, the easier it is to magnetise and demagnetise. And remember, soft iron is nothing to do with it being physically soft. It's still very hard, but it's to do with it being magnetically soft, which means it can change its magnetic properties quickly. This leads us on to talking quickly about the national grid. Here's some numbers for the national grid. For the exam, you need to have an idea of the numbers. Power station might generate the electricity at a potential difference of 25,000 volts. We need to increase this to send it along the transmission lines. The reason we do, this is some year 10 revision or 9 revision, the reason we do is that we want to minimise the power loss in the grid. The higher the current, the more power is lost due to heating of the wires, the overhead wires. So we transmit it at a high voltage and a low current. So you might transmit it at 275 kilovolts for supergrid, about 132 kilovolts for the national grid. 33,000 volts for heavy industry using large machinery might need quite a high voltage. Railways use about 25 kilovolts, so you drop it down using step-down transformers. 11 kilovolts for lighter industry, and finally when it gets down to us at home, the voltages drop down to 230 volts and the current is increased accordingly. AC, remember, has to be used for this whole system to work. The national grid relies on step-up, step-down transformers. AC has got to be used for obvious reasons, but at home very often our devices need direct current. So to do that we use diodes to what we call rectify, which means it converts AC to DC, makes it only positive, and then capacitors are used to smooth it. Instead of having a changing direct current, we use capacitors to smooth out. So to finish, we just need to consider in a bit more detail why the grid system is used, and we've got this basic idea that if you transmit electricity at a high current, then that high current causes a heating effect, and that heating effect leads to energy losses. So what we do, we increase the voltage, which reduces the current and hence decreases the energy loss. We need to take this argument just a little bit further. We need to consider the equation P equals IV. If we increase the voltage, then we reduce the current, we know. But we need to involve now that our AS equation, that the power loss through heating cables is equal to I squared R. So P equals I squared R, and I'm going to insert I equals P over V and square it. So we end up with the total power lost is equal to the power transmitted squared, because we've squared it in the formula, over V squared, because that's the other part being squared, multiplied by R. So I've inserted into this I squared, I've inserted this squared. So we end up with the power lost is equal to the power transmitted squared, multiplied by the resistance, divided by the voltage squared. Okay, let's put some numbers into this. For a given power to be transmitted through cables of resistance R, the higher the voltage is, the smaller the power lost. If you're transmitting electricity, you need to transmit a certain amount of power. That's going to be so many gigawatts, so you can't change that. You've got to transmit that amount of power. You're going to be using cables or a grid system with a particular resistance. That's fixed once it's been designed and implemented. You can't change that. So all you've really got to mess about with here, you can see, is I can consider the voltage. So we want to minimise the power lost by changing the voltage. If we make the voltage higher, if we increase the value of V squared, then the higher V squared is, the smaller P lost is. And remember, P transmitted and R are going to be fixed. So this is what we need to do. A couple of examples. If we use this formula, what is the lost power of transmitting 1 megawatt of power through cables of resistance 500 ohms at 25 kilovolts? So if we just put all this into our formula, so we've got 1 megawatt, 1 times 10 to the 6, multiplied, we've got to square that, multiplied by the resistance of 500 ohms, then we've got to divide that by 25 kilovolts squared. If you put all that into your calculator, you should end up with a power loss of 800 kilowatts. That's 800,000 watts. What is the lost power of doing the same at 400 kilovolts? So that was doing it at 25 kilovolts. This is about the voltage that a power station will produce. So we lost 800 kilowatts in doing it this method. If we now up the voltage to 400 kilovolts, let's see what happens in the equation. Well, we've got the same across the top, 1 times 10 to the 6 squared times 500, but we're now dividing it by a higher value of V, 400 times 10 to the 3. We're also squaring it, so we're getting a squared effect of that higher voltage, and our answer comes out to 3.1 kilowatts. And you can see the significant difference between 800 kilowatts if you transmit it at 25 kilovolts, or 3.1 kilowatts of power loss if you up the voltage to 400 kilovolts. So to finish, we'll just do a couple of questions. An ideal transformer with a primary coil of 3000 turns provides a 9 volts AC output when the input is 230 volts. How many turns must there be on the secondary coil? Okay, we're just going to use the ratio of voltages to turns equation, which is up here. Vs over Vp is equal to Ns over Np. If I rearrange that for Ns, I get Ns equals Np times Vs over Vp. If I put in my numbers in, number of turns on the primary was 3000, 9 volts is the voltage on the secondary, 230 volts is the voltage on the primary, and if you put all that, you go to your nearest whole number, which is 117 turns there must be on the secondary coil. A transformer has a primary coil with 60 turns and a secondary coil with 5000 turns. Calculate the primary voltage needed for a secondary voltage of 230 volts. Again, I'm going to use my Vs over Vp equals Ns over Np. This time I'm rearranging for Vp. So my Vp is going to be equal to Vs times Np divided by Ns. That's a simple rearrangement of this. I'm going to put my numbers in. My voltage on the secondary is 230 volts. It says here for a secondary voltage of 230. My number of turns on the primary is 60, and my number of turns on the secondary is 5000. Again, shovel that into calculator, and you should come up with an answer of 2.76 volts. 2b, a 230 volt 24 watt lamp is connected to this transformer. Assuming the transformer is 100% efficient, calculate the current through the secondary coil and the primary coil. With the secondary coil, we know that current is power divided by voltage. So on the secondary coil, we know it's a 24 watt lamp at 230 volts. So if we just do P divided by V, we get a current in the secondary of 0.1 amps. To do the same in the primary, the power, we know it's 100% efficient, so it's going to be the same power, 24 watts, but this time we need to just refer back to our answer here, and we need the voltage on the primary coil, which is what we calculated here, as 2.76 volts. So 24 divided by 2.76, this is 8.7 amps. So the primary current is 8.7 amps, the secondary current is 0.1 amps. So the current is going down, which means this was a step-up transformer.